Hi everyone, welcome to AMC 10 Prep Class 1. I'm Anna. And I will write my notes today. So before today's class, I just want to say that please check your email and check the WeChat group because I will post all my notes and this recording into the WeChat group and through email. In addition, I will host a Q&A section every Sunday from 6 to 7 PST or 7 to 8 MDT every Sunday. So if you have any questions for homework or anything I have addressed in class, you're welcome to come. You can also message me anytime you want on WeChat or through email if you have any questions. So let's start our today's lesson. So today's class we will be talking about triangles. Oh, also in addition, I will send out better writing notes for every class. So discard my bad handwriting every time I write notes. So the three topics I will talk about today is ways to find area of a triangle, and then angle bisector theorem, and last, similar or congruent triangles. So let's get into our first topic, ways to find area of triangle. The first way, obviously everyone knows, is the base and height one. So base times height over 2 should equal to the area of a triangle. So I'm not going to talk a lot about this, so I move on to the next one, which some of you might know is this formula. So in a triangle, if I label this A, B, C, and the side length is A, B, and C, I make a height, which is H, and label this angle theta. The area of a triangle can be written as A times B times sine theta over 2. So I'm going to write a little proof of this theorem. So everyone knows that sine theta in this diagram should be H over A. So H should be A times sine theta. So the area of triangle ABC, also a note here, this is like one of my personal preference. I write area like this. So this is an indication of area, and this is triangle ABC. So just take a note of that. I have very weird handwriting. So the area of triangle ABC is base times height over 2, right? And since height equals to A times sine theta, we can substitute H in here. So it's B times A sine theta over 2. And if we simplify it a little bit, it should be AB sine theta over 2. So this is where our second formula came from. Third one is Theorem's formula. So this is an actually very complicated formula. So here's a triangle. A, B, C. and then if I label this angle theta. So the area of triangle ABC will equal to square root of S times S minus A, S minus B, S minus C. And S is a symbol of A plus B plus C over 2. So in general, S is half of the circumference of the triangle, and the area is the square root of S times S minus A times S minus B times S minus C. Sorry, I made a typo right here. S minus C. So now, hopefully, you can understand this proof. It's a very long proof. I personally like the algebra way, and there's also a geometric way to prove this. You can search it up online, but I personally prefer the algebra way. So for triangle ABC, the first method is half base height, right? So, and through the second method, we know that it's half AB sine theta. We want to substitute sine theta into something else because in this formula right here, we don't have any angles in there, right? We only have the side length. So we wanted to substitute sine theta with something. So first, hopefully you guys know what cosine law is. Cosine law basically correlates an angle and its corresponding side length together in a triangle. Cosine law states that c squared equals to a squared plus b squared minus 2ab cosine theta. Therefore, 2ab cosine theta equals to a squared plus b squared minus c squared. So cosine theta equals to a squared plus b squared minus c squared over 2ab. The reason why we're trying to find cosine theta is because cosine theta, let me just copy this. Cosine theta, there's a way to find sine theta through cosine theta. Since sine squared theta plus cosine squared theta equals to 1, this is a general rule in trigonometry. Sine theta should equal to square root of 1 minus cosine squared theta. And since cosine theta equals to this big chunk of thing, we can substitute it back in. 1 minus, too big of a parentheses. A squared plus b squared minus c squared for a squared b squared. Then we simplify this a little bit. So 2ab square root of 4a squared b squared, a squared plus b squared minus c squared, and the whole thing squared. Hopefully, you guys know this formula. X squared minus y squared should equal to x plus y times x minus y. So if we plug this in, we can see that x is the 2ab squared, which is 4a squared b squared, and the y is obviously the a squared plus b squared minus c squared. Therefore, this formula, the sine theta could be written as 2ab square root of, what happened? Okay, 2ab, square root 2ab plus a squared plus b squared minus c squared times 2ab minus a squared minus b squared plus c squared. Just to simplify things, I'm not going to write the denominator from now on, so the numerator equals to this whole big chunk of thing. And then let's have another page. Okay, the numerator will equal to, let me just copy this. So hopefully we can see that if we group these two together, x plus y squared is x squared plus 2xy plus y squared. Hopefully you can see that these two format is very similar. X minus y squared is x squared minus 2xy plus y squared. So the second one is correspond to this one. So x is a and y should be b. So the numerator could be written as a plus b squared minus c squared times c minus a minus b squared. And now we go back to the first formula we have seen, which is this one. So x squared minus y squared equals to x plus y times x minus y. So this formula could then be written as a plus b minus c times a plus b plus c times c minus a plus b times c plus a minus b. Therefore, sine theta will equal to, remember we have the denominator of 2ab, and our numerator became a plus b plus c times a plus b minus c plus c plus b minus a times, sorry, I keep saying plus, it should be times, a plus c minus b. Because, also just a note of my own handwriting, this sign means because, and this sign means therefore. Okay, so because our area of triangle ABC is half AB sine theta, right? So if we substitute the sine theta in, we can see that the AB cancel out, right? So now it became this square root of all this big chunk of thing over 4. So now we know that the small s we define is a plus b plus c over 2. And then our area formula is 16. If I move the 4 into this root, it should be a plus b plus c, a plus b minus c, b plus c minus a, and a plus c minus b over 16. Everything is in the square root. Then we can see that if we group things together, so the first group is, 16 is 2 times 2 times 2 times 2, so we can group it as half a plus b plus c times half a plus b minus c times half b plus c minus a times half a plus c minus b. then we can see that this part is basically S. This part is S minus C. This part is S minus A. This part is S minus B. Therefore, our formula became S times S minus C, S minus A, S minus B, which is exactly the same as this one right here. Yeah, so that's the proof for the theorem's formula. It's a very long proof, and it includes a lot of factorization, a lot of splitting, a lot of algebra in general. So if you didn't understand that, that's totally fine. There are so many other ways to find the area of triangle. So the next way I'm going to talk about, which is the fourth way, is using in radius. This method includes using a circle. Oh no. Okay. Sorry for my ugly drawing circle. So here's a triangle ABC. If you're provided with the in radius length, which is represented by R in this case, the area of this triangle ABC could be written as R times A plus B plus C over 2. So here's a little knowledge about triangles in radius. So an in radius is basically a circle inscribed in a triangle AB. Not in radius, as in circle is basically a circle that is inscribed in triangle ABC. So all these three sides, AB, AC, and BC, are tangent to the circle. So since circle O, this point is O, circle O is tangent to AB, AC, and BC, every angle, so these angles, are 90 degrees. This is the definition of tangent. So now, where does this formula came from? We can separate the big triangle ABC into triangle AOC, which is this part, and OBC, which is this part, and the empty one, ABO. So triangle BOC, which is the green one, should equals to A times R over 2, which is basically base times height over 2. Triangle CAO, which is the red one, should equals to B times R over 2. And triangle ABO equals to C times R over 2. And if we plus all these three triangles together, we can see that it equals to triangle ABC. And we plus the left side plus the right side, so AR over 2 plus BR over 2 plus CR over 2. And since every single item has R over 2, we can factor that out. So it's R over 2 times A plus B plus C, which is our formula. The next one, number 5. Since we have in radius, we can also use circumradius to find our area of circle. Circumradius is basically the circle a triangle inscribed in a circle. So it's like a complete opposite of the in circle. So here's a triangle ABC with side length small a, small b, small c. And here is the in radius. I mean circumradius. Sorry, I keep saying things wrong. Circumradius should all be equal. This is O. So the area of triangle ABC should equals to A times B times C over 4R. Proof for this, again. The proof for this needs sine law. Before we talk about cosine law, right? Which is, here, let me write that, cosine law. These are the two most important laws you have to remember for trigonometry. Cosine law is c squared equals to a squared plus b squared minus 2ab cosine theta, which the theta is correspond to the angle side length c correspond to. So if in this case, if side length c is this one will be the theta. The sine law, however, is a over sine a equals to b over sine b equals to c over sine c. ABC, this big ABC, is the angle, and the small ABC is the side length. Most people know this part about sine law, but there's actually an extra version and this of sine law, which this entire thing equals to 2r. So a over sine a equals to b over sine b equals to c over sine c equals to 2r. Most people know the first bit, this bit, so I'm only going to prove the last bit. So in general, I have to prove a over sine a equals to 2r. That's our goal. Let me copy the diagram. Yeah, okay, so in this diagram, O, circumcenter, and let's make a line D, OD. D is on BC, that OD is 90 perpendicular to BC. Okay, the reason why I make this line is because if we look carefully, triangle BOC is isosceles triangle. So OB equals to OC equals to R, both of them equals to the circumradius. Triangle OBC, triangle OBC is isosceles triangle. Therefore, if we just take this triangle out and then we draw a 90-degree line here, it is pretty easy to see that like the red triangle and the green triangle are exactly the same, right? It's just like you flip, sorry, I forgot to write D. It's just like you flip triangle ODB to the right side and it became ODC, right? Because these two lengths are the same. A notation we use for exactly the same or a congruent triangle is this one. So this symbol right here. So ODB is exactly the same as ODC. Just a note, this sign means that the two triangles have exactly. Is that how you spell it? Oh, I spelled it wrong. Exactly same size and same shape. Since we know that these two triangles are exactly the same, we know that BD equals to CD because these two lengths should be the same, right? We flip this. BD equals to CD equals to A over 2 because the side length here is A. And since these two are equal, they should be exactly the same. And the entire length of BC is A. So BD should equal to DC equals to A over 2. And angle BOD equals to angle COD. If you look in a circle, there's a theorem that says that if, this is the center, these two angles has if this angle equals to theta, the angle that's connecting to the center should equals to 2 theta. So using this theorem, we can know that 2 BAC equals to BOC. So this angle, I should probably change the color. Well, okay, BOC is this one, and BAC is this one. You see that it is exactly the same as this diagram right here. So 2 angle BAC equals to angle BOC. So angle BAC equals to angle BOD equals to angle COD, and all of them should equals to theta, which theta is this angle right here. So BAC obviously equals to theta, right? BOD, since it is half of BOC and BOC equals to 2 theta, half of that should also equals to theta, and same idea for COD. Then, let me flip a new page. Okay, let me just copy the last sentence down. BAC equals to angle BOD equals to angle COD equals to theta. And let me copy this diagram here. Okay, and if we use this triangle right here, let me highlight it, BOD, this really small triangle right here, and if we take it out, it's 90 degree, A over half, this is R. Using triangle BOD, sine theta, which is theta is this part, right? So these are all theta. Sine theta should equals to A over 2 over R, which is A over 2R. Therefore, if we simplify this a little bit, 2R should equals to A over sine theta. And what is theta? In this diagram, theta also equals to angle A. So it should equals to A over sine A. So yeah, that proves our theorem. So let me write the entire sine law again. Is A over sine A equals to B over sine B equals to C over sine C, and the entire thing equals to 2R, where R is the circumradius. So since we proved this part, let us finish proving our fifth way to find it. So area equals to ABC over 4R. So let me just copy this. Okay. The basic form is half AB sine theta, if we remember from our second way. And sine theta from our last page should equals to A over 2R. Okay, let me just draw a diagram just in case we have so many thetas moving around and it's... Let me just switch a notation because it's really confusing. Okay. So, our second formula states that S triangle ABC equals to half AB sine theta, right? However, the theta is this theta. So these two theta, this theta and the theta we have for our last page, is not the same one. Therefore, let us change our notation a little bit. So this should equals to sine C. Let me erase the theta right here. Sine C, this big C just indicates this angle right here. And what is sine C? We know that A over sine A equals to B over sine B equals to C over sine C equals to 2R, right? And we want to know what sine C is, so we can just have the last bit of this formula. So C, sorry for the confusion if you're confused which C is the big one, which C is the small one. The upper one is the small one, the bigger one is the lower one, which indicates the angle. So C over sine C equals to 2R. Sine C should equals to the small c over 2R. Therefore, this formula S triangle ABC equals to half AB sine C equals to half AB sine C equals to this thing. So C over 2R. So ABC over 4R. So that's our fifth way to find the area of the triangle. And our last way, coordinate / shoelace. This is just a really interesting method of how to solve a triangle in a coordinate. And unfortunately, I don't have a really nice proof for it. So, yeah. So, if we have a triangle, and this triangle have coordinates -2, 4, 4, 3, -4, and -3, we can find the area of a triangle like this. So we pick a point, let's start from 2, 4, and we just write the coordinates clockwise. So, or counterclockwise, like whatever you want. So -2, 4, 3, -4, -3, and we end with 2, 4 again. So this part is very important. You have to write -2, 4 again. And then we times it. 2 times -3 is -6, and then -12, -16, and we times it the other way. 16, -12, and 6. Then we add the left side together, add the right side together. So the left side, 16 minus 12 plus 6 should equals to 10, and the right side, -6, -12, and -16 should equal to -34. Then we minus this. So 10 minus -34 should be +44. Then, this means the absolute value, so make sure you take the absolute value. So 10 minus -34 is +44. And remember, the last step is always use -44. You have to divide it by 2, which is 22. So the area of this triangle should be 22. Also a note that this shoelace method could also be used by a pentagon or a rectangle. As long as you know all the coordinates of the points, you can use this method. So this method is a very interesting method if you have a coordinate system. Then we finish our ways to find area of triangle. There is 6 ways in total, and you can pause the video or replay any part you want if you didn't get anything. Feel free to message me as well. So next part, we go into the angle bisector theorem. This theorem, as you might get from the name, which is angle bisector, is for bisecting an angle. Bisecting means that splitting an angle in half. So in this case, I split angle A into 2 thetas. Okay, so in this triangle, we have this 2 thetas. A is the length, B is also a length, C and D are length of this part and this part. So this is a triangle, and the angle bisector theorem basically states that C over A equals to D over B. Just to clarify, this C right here is length. So the angle bisector theorem, even though it sounds that it is about angles, it is actually all 4 of these are length of the triangle. So C over A equals to D over B. And now I will go over the proof. Some of you might wonder why am I going over the proof, because it's very long and very complicated, whereas the theorem is just very short and neat, and you don't really need the proof if you are in AMC competition. But the reason why I'm going over it is because if you only know the theorem by its surface, it's really hard for you to utilize it and just even remembering it in the competition, because AMC is not an open book competition. So if you don't go over the proof and understand why the theorem came from, it's hard for you to actually utilize it and simply memorize it. So yeah, let's go over the proof. This proof also utilizes sine law. So A over sine theta, if we look at this triangle, this triangle right now, A over sine theta should equals to, let's name this angle alpha. A over sine theta should equals to C over alpha, sine alpha. And if we look at this triangle on the right side, D over sine beta, if beta is this one, equals to B over sine theta. Then we can switch it around a little bit. So C over A should equal to sine alpha over sine theta, and D over B should equals to sine beta over sine alpha. And since alpha equals to 180 minus beta, sine alpha should also equal to sine 180 minus beta. Like I just add a sign to both sides of this equation. And sine 180 minus beta. If you know a little bit about trigonometry, you might know that sine an angle should equals to sine 180 minus that angle. So sine alpha should equals to sine beta. Like what I mean is these two parts, this part and this part should equal. In general, this is the rule that I use. I will just write it out. So sine 180 minus beta equals to sine beta. This is always true. So since we know that sine alpha equals to sine beta, we can substitute it in here. So C over A equals to sine alpha over sine theta, which is sine alpha equals to sine beta. So sine beta over sine theta, and this equals to D over B. So this is where our angle bisector theorem came from. So last bit, similar / congruent triangles. Okay, congruent, we actually talked about this a little bit earlier in this part. Oh no, where did I wrote it? Oh, here. In this part. This sign right here just means congruent, which means that it has exactly the same shape and same size. So this is the sign for congruent, and as you might guess, congruent, there's an equal sign underneath it, but similar, there's just this squiggly line without the equal sign. Similar triangles basically means that same shape, but not necessarily the same size. And congruent means that it has to be the same shape and size. So as you can tell, congruent is actually a very special type of similar triangles. So let me just give you an example. So this is similar triangle. Hopefully that looks similar enough. And the notation is, if this is ABC and this A prime, B prime, C prime, the notation is triangle ABC similar to triangle A prime, B prime, C prime. And if it is congruent, also a note, it could be like any rotation. So if I draw my triangle like this, and if it's still similar, it is like, it could be similar. So like the rotation doesn't matter at all. So here is congruent triangles. It means like exactly the same. Yeah, sorry, like that doesn't look exactly the same at all, but you get the idea. So triangle ABC congruent to A prime, B prime, C prime. Also, a very critical note that all the angles should correspond to each other. So this A should correspond to this A. But what I mean is you cannot write like this. B prime, A prime, C prime. This is wrong. Let me just add this red to mark this. This is wrong. Do not write like this. Okay. I cannot go back to my pink. Okay, good. Last slide. I'm going to talk about a little bit more about similar triangles. Similar triangles is something AMC really likes to do. However, it doesn't give you like, it doesn't tell you like these two triangles are similar directly. it is in the question. So if AC equals to AC equals to CE, by notation I put a 1, 1 here, which means that AC to CE equals to a 1-to-1 ratio. And BC is parallel to DE. Can say that triangle ABC is similar to ADE. And I'm going to tell you 3 information we can get from the similar triangle. The first one is AC over AE, which is this one over this one, equals to AB over AD. This one over this one equals to BC over DE, which is this one and this one. And this is half. Because AC is 1, CE is 1, and add together, AE should be 2. So AC over AE should be 1 to 2. And the next information we can get from the similar is angle ABC equals to angle ADE, angle BAC equals to angle DAE, and angle ACB equals to angle AD. So all these 6 angles are just basically corresponding angles. So for example, ABC is this one, ADE is this one. So these two are the corresponding angles of these 2 similar triangles. The third thing you can get from is the area. Triangle ABC over S triangle ADE should equals to the side length ratio squared. So it's 1 to 2 squared, so 1 over 4. What this means is that this triangle over here and the big green triangle over here has a 1 to 4 relationship. Make sure you square the side length. The reason why we square it is because, in a triangle is base times height over 2, right? And for a similar triangle, it's basically like shrinking, right? So you shrink the height by 2 and you shrink the base by 2. And since you're timing them, you shrink this by 2 and shrink this by 2, you're shrinking by 4 in total. So therefore, the area ratio is the side length ratio squared. And basically, that's all I have for today. That's a lot of information, and since I wanted to scramble it in 1 hour, I actually talked really, really fast. So, make sure you pause the video or ask me questions, or press the replay button if you have any questions, because I go over it really, really quickly. And here is your homework for today. This is an AMC question. I scrambled from AOPS website. I won't tell you which one it is, so you guys won't go online and find it. But yeah, this is the question. You can screenshot it, do whatever you want for it, and then please send your answer in the WeChat group chat or email me. Don't be shy or anything. And yeah, that's the end of today's lesson. Really hope you enjoyed it. And please tell me any suggestions. Is it too hard? Am I going over it too fast? Or is it too easy? And yeah, make sure if you have any questions, come to the Q&A section on Sunday. Thank you for listening.